Hi, so I have some very interesting things to tell you about today. At least I think they're very interesting, and I hope that you will too. Now, first, we need to talk a little bit about some ideas about multiplication and addition in general, and how they're related, and exponentiation. That sounds like it's going to be very basic, but actually the discussion today is not going to be basic. However, we needed to talk about that first to get to, and there's some very interesting things there. Then, in order to get to some even more interesting things, in my opinion, about conic sections, and also continued fractions and algorithms related to continued fractions. So, in my opinion, getting to some very interesting questions at the heart of mathematics. And these really are my thoughts regarding some things that I'm studying. I'm sort of a hobbyist amateur. I'm not really an amateur mathematician in the sense that I don't have any published papers. Maybe someday I will. But I'm really more of a hobbyist. However, to be fair, when I've spoken to people who have even PhDs in math, actually, I don't mean this as a brag, but there's a lot of things that I know that they don't know, because they're typically very specialized, right? So anyway, let's get into it. And first, some fairly obvious things about, for example, that if you have some exponential stuff going on like this, as many of you know, this will equal x, e to the x plus y, and it doesn't have to be, the base can be whatever. I just chose the number e for fun. But yeah, obviously we have this addition rule of exponentiation, I guess you call it. So there's this interesting thing where when we start learning math, we sort of begin with addition. We learn how things add. And then we learn that if we add something to itself, 4 times, that this is multiplication. And then later, we of course learn that if you, let's say x is 4, if we did, let's call this operation A, and if we do A 4 times, I'm tempted to write a 4, but I don't really have the proper notation here. But we have some operation A. We do it 4 times, so we get 4 to the 4, and so on. So all I'm saying is, obviously, we build the concept of exponentiation from multiplication, which is built from addition. So we have addition being used as the fundamental building block to give us multiplication, which then is a fundamental building block to give us exponentiation. Exp, when you write that, it sounds like e to the whatever, but I mean exponentiation in full generality, so I'll write it out. Exponentiation. I give up. So we build it in these ways, and then we get back to finding a rule with addition there, right? And so we've kind of come full circle in some sense. And so one of the things I'm sort of interested in, and I'm absolutely 100% sure this has been very thoroughly studied, but if somebody knows who studied it and where the papers are, please direct me, because I don't even know where to begin. But in some sense, there's like a nested, like those Russian nested dolls, this kind of situation going on. Because now that we have addition again, we can probably repeat this process again and start talking about, you do this a certain number of times, and then it acts like multiplication, and so on and so forth. So we can build back to exponentiation again, a higher level of it, and then find some further higher level addition rule and then just keep repeating the process, right? And apparently if you take something to the, keep doing to the x power, to the x power, to the x power, or whatever, n times, this is something that's studied, and I think it's called tetration, something like that. And so I'm sure this stuff has been studied, and there's this, I mean, it's rather obvious, right? There's this like this nested doll sort of structure going on, and I'm very curious, basically, and I'm gonna get, I think this is probably well studied and well known out there somewhere, but I'm gonna get to more original, quote unquote, ideas later, which I don't pretend that I'm the first person to ever think these things, but I think, yeah, if you're looking for something more original, I think you'll find it later in the video. But anyway, so this I'm sure has been studied, and to talk a little bit further about it, so there's some kind of structure here, some kind of symmetry, and possibly some kind of manifold that we could, I imagine we could build, because there's this symmetry, this within this nested doll structure, you have some form of symmetry, and the symmetry is a very interesting thing. There's this quote, can I find it right now? This very interesting quote. Probably not. Dang, I was gonna find it before I started this video, but I'm afraid I might edit it if I have time to give you this quote about symmetry. And okay, I think I found it. Yeah, here it is. To define the idea of, so this quote is from Judith Weschler. No, it's from Philip Morrison, an article called On Broken Symmetries, which appeared on Aesthetics and Science 1981. Okay, that's the quote. So that's where it's from. So to define the idea of symmetry is certainly not simple. I shall not try to make an all-encompassing or precise definition against which a contradiction can quickly be brought. The idea is still alive and growing. We don't know all that the concept implies. I like best the idea of the 17th century philosopher Leibniz. For Leibniz, symmetry is related to the indiscernibility of differences. Once you walk into the hall of a Palladian building, you can't quite remember whether you turned left or right. So if we got lost in the process of this, deep down in the process of this nested doll structure, there's a symmetry in the sense that we sort of vaguely, we forget how far we went down the rabbit hole, so to speak. There's some kind of symmetry right there. So can you build some kind of weird manifold of some kind, or there's some kind of structure here? Is it a manifold? Maybe. I don't know. I don't even know what to search for. So maybe a math guru out there can share with us in the comments, let us know what to even look for to sort of explore this kind of symmetry. And maybe there's some kind of Dinkin diagram that corresponds to this situation, if you know what a Dinkin diagram is. Anyway, so I think that's very interesting. Now I want to go further to talk about some conic sections. I think, and some other things. It will tie into this, what I've discussed so far. Though I might, it might be sort of in the background somewhere there. I don't know that I can explicitly tie it in. And then there's also this stuff with continued fractions that I wanted to talk about. So, yeah. So let's introduce the idea of continued fractions a bit. So for example, gosh, introducing this stuff is going to be sort of, to do it impromptu is quite a tall order. But basically, for example, the square root of 2 we can find, and I may be able to demonstrate this here today, or perhaps not, but we find, if I remember correctly, that this is equal to this infinite continued fraction, where you continue that pattern forever. Very interesting. Now, how can I demonstrate this? If someone's skeptical, I'll try to. This is off the top of my head, so I'm not sure if I can do it, but we could, let's see, +1 and -1, right? And I think, maybe there's, you know what? I think there's a 1 here out in front. And so 1 plus √2 minus 1. And then we do the good old trick where we multiply top and bottom by this, which is, we can do because we're multiplying by 1, right? And now we get 1 plus, on the top, we'll get 2 minus 1. On the bottom, we just have √2 plus 1. And let's see here. Note that, so this is √2 equals this. I'm going to rewrite this. So √2, I'm going to write a little arrow. √2 equals 1 plus 1 over 1 plus √2. Now notice that we have this part and this part are the same, which means that this thing can be substituted back into here. It's a recursive process, essentially. Recursive iteration. And so we get, when we do that, we have 1 plus 1 over 1 plus this whole thing in here. 1 plus 1 over 1 plus √2. And then we can continue the process once again, ad infinitum. We can do it forever. So what we end up having is, at some point we get a 2 in there somewhere. So left as an exercise to the reader. Oh, you know what? Because this becomes 2. That's why. 2 plus, and it's the whole process is going to repeat like this forever. Okay. I slightly skipped over it. You could do 1 or 2 more iterations to make it a little more clear, and I invite you to do so as an exercise. It's quite nice. Anyway, so we see this kind of infinite continued fraction, and this is interesting in its own right. For example, I mean, numbers like e and pi can be reformulated in this infinite continued fraction form in a way where you see some kind of structure there. Whereas for pi, it's 3.14, 159, 265, 35, 89, 79, 323, blah, blah, blah. And these digits seem sort of random. Of course, there has to be some pattern there, but it's not immediately obvious, right? And so there is some kind of, you can look it up, there's some kind of version, a continued fraction version. However, so this continued fraction here is what's called a simple continued fraction. And it's called simple because there's a 1 here. All these numerators are 1s. And we call that a simple continued fraction. Now, for the pi continued fraction, and this may or may not have to do with the fact that pi is a transcendental number, right? It's pi and e are transcendental numbers, and they are special in some way. But the numerators are not, well, actually there's a couple different versions. So I think there might be a version with the numerator being 1. I forget. And I don't have the pattern off the top of my head. Let's see if we can find it here. Pi as continued fraction. Let's see if we can find the pattern. So, yeah, let's look at this. So, come on. I want to zoom in for people. You know what I mean? It's an SVG file. I don't know what program that's going to open up in. But Hopefully you can see it well enough. Oh, so that's interesting. So this is a different form. 4 over 1 plus... yeah, see, there's different versions. It's very interesting. And I need to study it a lot more myself. But you see that we have this pattern where it's squared. So this one says 3 plus 1 squared over 6 plus 3 squared over 6 plus 5 squared over 6 plus 7 squared. And it looks like... So here it says the pattern is 3, 5, 7, 9, 11. So yeah, it's not prime numbers, it's just odd. It's odd numbers being squared. So it's very, very curious. Now we can also do the same thing for E. It's a little bit simpler, actually. Napier's number. E is often referred to as Napier's number, which makes it a little more searchable. So let's see this one. Nice and big. This is a different pattern than what I'm used to. So E. Let's just type E. So here I think you can see the pattern, though it's not big enough. Sorry about that. But so here we have it as a simple continued fraction, I think, because all the numerators are 1. And we have the pattern on the left is 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, 10, 1, 1, 12, and so on. So it's like it's counting by even numbers, and you have these ones. So it's very, very intriguing, I think, and it's sort of tempting to try to think about some of these numbers, or just all numbers, in terms of continued fractions, so we can try to find a structure, right? A structure of these numbers, rather than 3.1415926 blah blah blah. If we look at the continued fraction forms, we have more structure to work with, and there's a lot of interesting stuff to try to dive into. And I think continued fractions are not... They should be studied much more than they are. Of course, many people value them highly and are very intrigued and dig into them, but I think they need to be... really, they should be taught in high school. I certainly didn't learn them in high school, but I think it would really get people interested. Now, so I won't go through it in detail, but basically, actually, Mathologer has good videos on this stuff, but all rational numbers expressed as continued fractions, the continued fraction will terminate at some point. It will not go on forever. So there's this, I suppose it's a theorem, or correspondence, where basically rational numbers, so let's say P and, let's just say P and Q or whatever. Well, I'll express a rational number as P over Q. A rational number can be expressed as a ratio of 2 integers, essentially. So, such that P and Q are elements of the integers. There are integers. So this will can be used to describe a rational number. And for every rational number, we have some continued, at least one continued fraction that terminates. And the converse is also true, that if you have a continued fraction that terminates, you can create a rational number from it. And also, furthermore, if a continued fraction goes on forever, I think that means that it is irrational. I'm not totally sure about that. It might be, I could be wrong, because like 0.999 forever, we basically say that that's equal to 1, and maybe you can express this as a continued fraction. I'm not sure, so I need to look into that more. But this is all very interesting stuff in its own right. And further, there's further correspondence to logarithmic spirals. And again, I'm not going to go into super detail on it. I would refer you to Mathologer's videos on continued fractions and spirals. Mathologer. So there's a type of spiral called a logarithmic spiral, and among them is one specific version of them is the so-called golden spiral. The golden spiral is a very specific example of the logarithmic spiral. And you know, the number phi, sometimes usually it's written like this, phi or phi is I forget what it is exactly, 1.7 something or something like that, but as a continued fraction it is equal to, like, kind of the simplest one you can imagine, just all ones. And in some sense, this can be thought of as being the most irrational number, because it has, so from these continued fractions, when they, well, so suppose you have an infinite continued fraction, you can sort of truncate it, cut it off at a point, and this will give you a decent, so you can then calculate a rational number from that, a ratio, and that number will provide a pretty decent approximation of whatever irrational number you were working with. So with pi, for example, you can get nice approximations of pi by using this. So that's very interesting also in its own right, that we have now a system of making good rational approximations of irrational numbers. So that's interesting from sort of a computer science point of view. That kind of makes you wonder, is this continued fraction system, are there good algorithms here? Are there useful things for approximating numbers like pi? I mean, pi, e, these are very important numbers. And, well, of course, people have figured out the good rational approximations using this system. So it's sort of been done. So you don't need to do it yourself. You can just go look it up. But there's tons and tons of irrational numbers. So if you were doing some kind of physics-related thing or math-related thing where you had a lot of different irrational numbers and you needed to calculate them accurately, this is where what I would look to for approximating irrational numbers. If you have some kind of algorithm or program that needs to do that. And sort of bonus tip, Lisp is an excellent language for this kind of stuff. Definitely look into that if you're interested in it, but I'm not going to talk about it more today. Lisp is sort of special in how it does some things. So, okay, so continued fractions, very cool, very interesting. These spirals, logarithmic spirals that correspond to them, very interesting. I'm not sure, and in my head, it's an open question, how these transcendental numbers like pi and e, do they have spirals? I don't think that I don't know. I'd like to find that information. It's probably out there somewhere. Can we say, because I know the logarithmic spirals can be used to represent irrational numbers, infinite continued fractions of the irrational number form. So phi is an irrational number, but it is not transcendental, whereas pi, and I'm pretty sure e, correct me if I'm wrong, but I'm pretty sure e also is transcendental, whatever that means. And when you look up what it means that a number is transcendental, I'm spelling it wrong. Here we go. Basically, I think it cannot be described algebraically, so phi can be written, I believe it's this, if I remember correctly, or there's a minus sign there, and so that's an algebraic expression, whereas pi and e cannot. probably through some infinite series of some kind, right? Because like pi over 6 is equal to this series, if I remember correctly. Oh, there should be a dot 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 on this side. But, right, so I think we can represent them sort of as infinite series or infinite polynomials, but not in a neat algebraic expression like this. So I think that's what it's about, you know, being transcendental. But I'm sure there's people out there who know much more than I do about it. So all of this is already kind of neat and interesting. But then when you get deeper into it, I think the computer science angle here is very interesting. There's some stuff there that's quite special. And, you know, I sort of mentioned it about these algorithms, that this is sort of... so you can view it as a logarithmic spiral, infinite continued fraction, logarithmic spiral, but there's also some kind of infinite process going on here. So there should be some kind of algorithm that corresponds to it. At least that's what I think. So most mathematicians are not that interested in these kinds of algorithms so much necessarily. They might be, but it's really in the computer science department where this stuff is super, super important. And there's some guy who in, I think, the 1970s went into the sort of computer science detail about these continued fractions and algorithms related to them. So like I said, this might be very useful in some very specific contexts. It's not going to be useful if you're building a game or pretty much any like normal programming. It's not useful. But if you're working with a supercomputer, building some kind of physics simulation, it might be important, right? Having precise, for example, the square root of 5, square root of 2, having precise algorithms for representing these. So there's something special that happens where, like, you can use these numbers. And so normally what we would do in a computer is we have, for example, let's say you have a 64-bit integer. It could be signed or unsigned, meaning positive or... so unsigned is only positive or 0, whereas signed means you can have negative numbers, but you get roughly half as many possibilities, if that makes sense. So you would just store it in what's called a float. It's just a decimal number, and so it has a limited accuracy. Obviously, we can't store a number with infinite accuracy. However, what this continued fraction business allows us to do is basically you could have a variable, and let's say phi as an example, because it's going to have this root 5. So you have this variable, and you can compute things in a lazy manner. You can, instead of immediately computing this to some accuracy and storing it in storage somewhere or in memory, you can just have this in your program and calculate it as far as you need to when you need to. So that is through this continued fraction form. Basically, you represent this irrational number by this algorithm. And then, so the key word here, or phrase, is continued fraction arithmetic. Searching this will get you what you want. And so arithmetic. I'll spell that out for people who are not native speakers of English. Arithmetic. So this is the maybe the innovation that the individual did. I'll put information in the description of the video because I don't remember the guy's name. I'm gonna, it's something that I'm looking into further. There's a bunch of, you know, he has, I don't know if it's really a book, I feel like, but you can find it as a PDF, and other people have talked about it. There's something here where, for computational reasons, there's actually a logarithmic continued fraction, which makes computation sort of better and easier. And so we can do this. We can set up expressions in our program that uses numbers like phi, and then say at the end, if we need a result, then we can compute it to a certain level of accuracy using this continued fraction arithmetic. And you're not going to, so if you keep, like what a normal program would do is that you keep storing things to some level of accuracy, and then when you do arithmetic with floats, you end up more and more introducing errors, basically. And you'd have, if you needed something that's totally accurate, like if you're doing math, for instance, you want things to be accurate. You don't want to be introducing sort of cascading potential. I don't know if it increases exponentially, but like little errors popping up everywhere every time you store numbers. That would be bad. So what we want is, we have our program, it runs, and it, at the end, maybe it outputs some big expression with a bunch of numbers and stuff going on. And then we can calculate this to a specific accuracy, and then we can say for sure, up to whatever number of digits, this is accurate. So that's the goal, right? And we can do this with this this technique of continued fraction arithmetic. Now, it is not sort of the processors that we have, the GPUs and so on, are not optimized for this sort of thing, because I think you end up with a lot of division, and our processors are not really optimized for a lot of division. This division is, the operation of division is something that really is computationally expensive, basically, compared to addition and multiplication. So, and I think, I don't know exactly, but this logarithmic continued fraction is a way to try to make things sort of more computationally reasonable, so we can get things done within somewhat of a reasonable amount of time. But here, I mean, the emphasis is on accuracy more than the amount of time for the program to complete. Okay, so that's all cool. That's all very interesting. Now, let's talk about the conic section stuff. And somehow I think this relates. Everything I'm talking about today is all sort of interconnected. And it really, so let me preface this by saying that I believe in going back to fundamentals. For example, take it for example, vectors and matrices. Some people will be, have a bit of an attitude and be like, vectors and matrices, they're really simple, real basic. Why do you need to think about them more? Well, in the world of matrix theory, you have the special linear group. You have SL2C. Okay, if I want to direct you towards something that's complicated, you have this group, which exists somewhere in the world of matrix theory. This thing exists, and in here you have fractals. Actually, you have the study of modular forms. Okay, crops up, and deep stuff from number theory. Okay, so if you want to be snide or smug or whatever, and sort of cynical, when I tell you, I feel like I don't totally understand vectors and matrices yet. If I say that and you sort of laugh, well, I'll direct you towards this. Are you a master of fractals and modular forms and all the stuff related to it? It's very deep. So what I'm saying is I routinely come back to vectors and matrices and try to think very deeply and sort of fundamentally, what is it really about? And in some sense, vectors as elements of a vector space, they basically, for me, are about addition, right? Because that's what if you tell me you have a vector space, that means really you have addition among the elements of the set, among the vectors, you have addition, and you have scalar multiplication. So I'll just write an S for scalar multiplication. And so the scalar multiplication, there's some kind of correspondence, or there's this question of, so why are conic sections so fundamental and important? The Greeks, obviously, the ancient Greeks took them very seriously. In Euclid's work, they are sort of the crowning achievement is this sort of classification of conic sections. That's my understanding. I haven't read it myself. And you see conic sections and the study of cones pop up in various areas. Like deep in the study of Jordan algebras, there's a theory of cones in some sense, like higher dimensional cones. It's a weird question. So this cone, and I'm sort of, this is sort of like the minus cone. Like if you had a hyperbola, if you cut this, you'll get a hyperbola, and this gives you both sides of the hyperbola. So you kind of need both sides of the cone here. You can kind of imagine it as like a positive part and a negative part. But one sort of interesting thing is, well, this is in 3 dimensions, or it's basically a 2-dimensional surface embedded in 3 dimensions. We have this sort of singularity here, which is in certain contexts sort of pathological, because like if it's differential geometry that you're doing, taking the derivative here at the center, the point here is going to be problematic for you, right at the tip of the cone. So this, you could call it a 2-dimensional surface embedded in 3 dimensions. So what's the analog in higher dimensions, higher dimensional cones? Thinking about that is sort of weird and a good exercise to occasionally try to do, thinking about higher dimensional cones. But for me, when I see this, I think of scalar multiplication. So imagine you have a unit circle and you scale it up or down. At its limit, when you scale it down, it collapses to a point, which is like this. And when you scale it up, you're going up the cone here, right? So you have kind of somewhere in here is a unit circle. And the choice of unit circle, of where it is, that's like choosing how big is the number 1. There's kind of a choice. Like if you're working with vectors and you have the dot, you're doing a dot product. So vectors, if you define a vector space, there's nothing in here about a dot product, okay? Some people sort of erroneously think that because you have vectors, you must have a dot product and a cross product. And that's quite wrong. For one thing, the cross product only works in 3 dimensions. There's an analogous thing in 7 dimensions. So it's a good mystery. Why 3 dimensions and 7 dimensions? You could spend months digging into the rabbit hole of that. That's a great rabbit hole. Why 3 and 7? But anyway, so the ordinary cross product only works in 3 dimensions. So it's very special, first of all. And the dot product is kind of special in its own way. I talked about this in my first video on differential geometry. We talked a lot about the dot product and how it's really a specific case of an inner product. Okay. So you can have a vector space and equip it with an inner product, and the dot product is just a specific case that sort of corresponds to an identity matrix that you're using as for your inner product. And this is basically the same as equipping the space with a metric. There might be a technical difference here, but as far as I know, it's you know, it's roughly the same idea. You equip it with an inner product, or we also say like a quadratic form. The quadratic form or norm, there's so many words that mean almost the same thing, but like maybe slightly different. It's sort of really annoying when you're learning this stuff. But these two words specifically refer to measuring the magnitude of a vector, basically. Because if you have this inner product thing, you can input two different vectors here, but this is specifically where you input the same vector twice, and so you're measuring the magnitude of the vector. So this inner product is sort of it's really a generalization of the concept of a dot product, and basically this is what you need as a starting point to get into general relativity, the study of Riemannian manifolds. So from a math standpoint, it's the study of Riemannian or pseudo-Riemannian manifolds, and in physics, it's from a physics point of view, we're talking about general relativity, you know, Einstein's gravity, which is the modern understanding that we have of gravity. You know, it's amazing because you start with this dot product, which you discover is useful. Dot product really, I think of it as about projection. So if I have I'll pretend these are random vectors. We'll call it, actually I want to make this one larger. So let's say it's P and Q. The dot product, you take an altitude, essentially. Now if these were, first it's easier to talk about the case where they're both unit vectors. So if they're both unit vectors, then taking this altitude, the situation is a bit simplified. So let's call this P hat and Q hat because we're talking about unit vectors. In this case, it's just the dot product is simply this projection. So here, P hat dot Q hat, the usual dot product, okay? Where we're using the identity matrix if you're talking about an inner product. So the usual dot product will simply be this projection of P onto Q. Sorry for those who are very familiar with this already, but that's sort of an important starting point here. If we're talking about a dot product, it's easier to look first at this case. And there's a symmetry here because they both have the same length. You could also drop the altitude in the other direction. And this picture is symmetric. You can draw a line here, a line of symmetry up the middle. And yeah, it's symmetric, which means, well, first of all, the dot product is symmetric in general, but what I've demonstrated here is that it's symmetric for the case of two unit vectors. Now, if we say, let's say our unit circle we've magnified a bit, and actually here, P is a unit vector, and Q is not. Q is a little bigger. Well, now our dot product is simply, we take, so here I'll do, so I'm going to indicate this as P hat dot Q vector because we said that P here is now whatever the unit length is here, 1. So here, what we do is this is equal to the dot product of the unit vectors, P and Q hat, times the magnitude of Q. So we've done the same story here, but now we've simply scaled it by the magnitude of Q because Q is bigger. Okay, and then for full generality, let's say this were the unit circle. Now, for p dot q as general vectors, we simply take the dot product of the hat vectors, the unit vectors, times the two magnitudes, p and q. I ran out of room. Wish I could draw over here. Right? So it's good when trying to understand what the dot product really is. It's good to sort of do this exercise of thinking first about the unit vectors, then change one of them in magnitude, and then think about if you change both of them times the magnitudes. P, I guess I write it like this, magnitude Q. Okay, and so this P hat dot Q hat was projection of one onto the other, and it was symmetric, and that's where this is also corresponds to the cosine of the angles, because the cosine of the angle between them, because that's just how that's projection. So for me, projection here is the fundamental thing, and I think it's useful to understand cosine and sine in terms of projection, and to understand the dot product in terms of projection. Projection for me is fundamental. So here you have some theta, and I'm not going to go more into it. If this is confusing, learn more about how cosine theta is like projection. So actually I will sort of just show that you can choose, you can just rotate this so that Q here, this is Q, is on this. We choose a coordinate system where Q corresponds to this x-axis, and then we have the P, and this is Q hat. And then we have P here, and so this will be cosine theta here when these are unit vectors, which is what we said we're dealing with here. This right here will be cosine theta, where this is theta, right? So if this is confusing, I have previous videos where I've talked about basics of trigonometry, so look to those if you don't understand what I'm talking about here. So that's why for the dot product you get this cosine theta times the magnitudes. I'll write it like PQ. Notice no arrow above them because we're talking about the magnitude. Cosine theta is the general dot product. Well, the general usual dot product, okay, is this. But it's also useful to calculate it from a computational standpoint. Usually you do it component-wise in the ordinary way. This calculating the cosine theta sometimes takes forever. So it's sort of a, can I call it a transcendental process? I don't know. Okay, so when I see this cone, I again think of scaling. And as we saw here, how you choose, you can kind of choose your, you basically choose how the length of what one is, right? Because we could be talking about 1 meter, or this bigger one, this is not to scale, but it could be like 1 kilometer. And when you do this dot product, you actually have to also do the dot product of these, I'll call them these unit vectors. What's the right word? I've run out of space. No. It's very annoying. Basically, if you want to be technical about it, vectors are not just these components. It's actually, really it's the components times some unit vector. For example, ij, call it whatever you want, e1, e2, whatever, x, y, okay. So they are, a vector is a linear combination of unit vectors. I think there's some more general theory where you don't have to have unit vectors here, okay? This kind of gets, again, towards in the direction of general relativity and that kind of stuff. We talk about coordinate systems that are not necessarily orthonormal. Orthonormal means that the normal means that they're perpendicular, the unit vectors are perpendicular, and the ortho means that they're perpendicular, and the normal means that of length 1. So in more general terms, we can talk about, you know, quote unquote unit vectors, or really a basis, right? This is really what I'm talking about, a basis. We can have a basis where it's not just orthonormal unit vectors. And actually that's basically a starting point for getting into general relativity. You talk about where you begin by studying how do you do coordinate transformations with general bases that are not necessarily orthonormal. Now, when you do a transformation, a linear transformation, sorry, I'm running out of steam a bit here. When you do a linear transformation, you can also think of this as a change of coordinate system, a change of your basis, right? So, yeah, that's sort of a starting point for a study of general relativity, and it's interesting. So you can choose 1 meter, or you can go way up at 1 meter as your unit, or you can go way up here and choose 1 kilometer as your unit. And so when you talk about a vector, you need to specify the units, basically. And what that means is that although we write column vectors, we typically write just the components, what we actually technically are doing is that we have 2 of something and 3 of something else, okay? So this is sort of like foundations of linear algebra, and this goes back to what I was saying, where you have to go back and think about these things many times, really, if you want to understand them on some deep level. Okay, so the scalar, I believe there's some kind of correspondence here in the picture, in the story, between scalar multiplication and moving up and down on this cone. We can go negative, and we go to the other side there. And then what about addition? So that's where what I'm looking into now is, what about addition? Can we take this whole story of vectors and matrices and the whole linear algebra story, and can we translate it into conic sections? Sort of a calculus or a alchemy of conic sections. Surely the scalar multiplication is right here, sort of vividly. But basically, I think you can take conic sections and decompose them into linear constituents, and then use that as a basis, pun intended, but sort of dual meaning intended, as a basis for constructing this with linear algebra. So I think there's, and probably this is well understood, that there's some correspondence here between the whole linear algebra story and sort of a calculus of conic sections. And in fact, being a little more concrete, if you look somewhere in here, Norman Wildberger has this channel, Insights into Mathematics. You can look in here, and there is he talks a bit kind of about what I'm talking about. So for a general conic section, you can represent it as a symmetric matrix. So because let's say we have some amount of x squared, we have some amount of y squared, we have some amount of... Should we do z squared? No. I don't know the details, and if I had more energy, I think I could recall it. But he writes his matrices like this. E... Sorry, it's... try to make it bigger. E, F, G. And that's how he chooses to write his matrices. That basically he represents a conic section as a matrix. And matrices are also vectors. Well, you can make a vector space from matrices. So I think it seems to be well known. What I'm saying is that we can maybe not have all of the linear algebra story, but definitely an important part of it corresponding with these conic sections. And it's just the whole symmetric part of it, because that's a symmetric matrix up there. So what's left is the anti-symmetric part. So I find that fascinating. And I don't know why I said sort of original in the beginning. Well, I've never seen someone talk about the notion... maybe I have. The notion of looking at this cone as representing scalar multiplication. But I think this is interesting. I don't know about you, but this whole idea of translating linear algebra into a story of conic sections. Now, but what about antisymmetric matrices? Those are part of the story. And this is an ongoing process of where I'm studying differential geometry, right? And one of the key words here is symplectic geometry, and I don't really... I've seen the word symplectic used to refer to basically like sort of quaternion stuff. Maybe like the the special unitary group, and quaternions and spinors, that kind of stuff. So I think it's related to that. Symplectic geometry. And there's Mobius geometry, and this might be kind of the same ideas, where we're talking about, I think we're talking about spinors, about the whole anti-symmetric side of this stuff. That, you know, a Mobius strip, right, is this band, or a Mobius band is this surface. I can't draw it. If you take a rectangular slice of paper, cut of paper, and you sort of twist it so that it has one half twist, and you tape it back together, right? This forms, there's one surface here. You can go around and around. And when you come back, you'll be on the other side of the paper, and you can go around. So this is called a non-orientable surface. And, you know, it's kind of famous, Mobius strip. You've probably heard of it. If you haven't, definitely check it out. Similarly, there are Klein flasks, or Klein bottles. The bottle is actually kind of a mistranslation from the German. But anyway, Klein bottles are a sort of a two-dimensional version of this. It's a two-dimensional surface that doesn't really embed properly in 3 dimensions, so it's kind of hard to imagine. It sits more elegantly in 4 dimensions. So this weird two-dimensional surface that sits in 4 dimensions, it's sort of like this, and I think there's a deep relationship between this and spinors and this kind of... So there's sort of this Mobius geometry going on. I don't know it well enough to explain it in a way that I'm confident will be technically correct in terms of the terminology and this kind of stuff. And I could be wrong about what is exactly meant by symplectic geometry. So I'm in the process of learning it. And I'll just show you symplectic geometry, the sort of the playlist that I'm looking at now. I don't know if it's a good playlist, but here it is. This one here. And he begins by going into differential geometry. They sort of begin the course with a review of differential geometry, and I mean, I've barely finished the first video. I looked at this before, maybe 1 or 2 years ago, but I didn't have enough of the prerequisites down at the time, so I'm coming back to it. I'm trying to learn differential geometry, so I'm very curious. Can I use, or is it well known that we can use some kind of Mobius geometry, this kind of thing, like a Klein bottle kind of structure, to get at this sort of anti-symmetric part that's sort of possibly missing from this story? Can we take this conic section and twist it? Can we embed it in a projective hyperbolic space, and so that this part is connected up here at the point at infinity, and then but also introduce a twist out there? Weird questions. Does it relate somehow to the octonions and or Clifford algebras? Deep, complicated questions. And why did I even talk about all this stuff in the beginning? Because I think somewhere in here is part of the story is the fundamental question of the relationship between addition and multiplication. And I didn't mention it yet, but in this story about continued fraction arithmetic, what's interesting is that one of the algorithms for addition and multiplication become the same algorithm at some point, somewhere in there. And so I'll put the link in the description if you want to find that. Maybe I'll tell you what page where it talks about the addition and multiplication becoming the same algorithm. And I think there's also something, you know, I'm being very hand wavy, but there's something about binary, which is also called, you know, mod 2 arithmetic, which is also called characteristic 2. There's something special that happens here with some of this stuff. Very hand wavy. That's been my experience. There's definitely special stuff that happens in characteristic 2. And I know that for sure because there's so many times when a math lecturer has said, for all situations except characteristic 2, blah, 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 blah. So there's very special things that happen with characteristic 2 or binary. And again, total hand wavy, just open question from my point of view. How does this relate to p-adic or l-adic numbers? I think there's not a lot of content out there talking about the relation, you know, p-adic continued fractions. But I think that's got to be important. I think the whole p-adic system is half of the story. And let me show you where I talked about that. I'm sorry, it's very hand wavy. That's part of why that's part of just what I do. This math will blow your mind. This one is where I talk about p-adic numbers. I don't have enough expertise. I wasn't expecting this to even... Most of my math videos get like 2 views, so I didn't know that I was going to get more views. But it motivates me to learn more about this stuff so that I can make proper content and learn it myself. But I think the p-adics or l-adics are an important part of the story. They have to be, I think. Somehow maybe they connect with this story of spirals. That's sort of a big question in my head. If you can think of numbers in terms of spirals, and I'm not sure if the transcendental numbers, if you can think of them as spirals, but there's all these connections between these algorithms with the continued fractions arithmetic. So I haven't dug enough into it to say... I know you can do it for irrational numbers, like the square root of 5, but what about pi and e? I kept saying that you can use it, but I'm not totally sure, because those are transcendental numbers. I really haven't figured out how and if transcendental numbers correspond to these logarithmic spirals or some kind of spiral. Maybe it's a spiral where you have to, as you get away from the center, it has to spread out more. Like maybe you can apply some kind of metric that changes with distance from the center. That will help. I don't know. So many questions, many things to look at. But I think it's interesting. Leave a comment with any thoughts, questions, musings, information if you know some stuff to tell me. This is just stuff. These are my thoughts. This is stuff I'm looking into. So I apologize that it's a bit hand wavy, I know, but I'm being upfront about that. And I'm sharing my thoughts because I want to. Maybe someone will point me in a direction and really help me out. And or maybe this will be inspiring to someone. Maybe there's information here that you found interesting. If you did, remember to leave a like. It will help me out. And I hope you have a good day. Best of wishes to you. Take care. Bye.